Hey everyone, what's going on? Welcome to Focus AI. So here in this video, we will see how we can fit our logistic regression model. So till now, we have learned that how to deduce the optimization equation or the optimization function for the logistic regression model. So on continuation of that, we will see how we can perfectly fit our logistic regression model. So this is the optimization function that we have derived. Right. So what it is doing, it is trying to find the minimum value of this whole summation. Right. So that is the motto of the optimization function. Now we will try to see each and every block of this equation or of this function, and we will try to get the idea how we can best fit our logistic regression model. Okay. So let's first concentrate on this part only, which is e to the power minus y w transpose xi. That means e to the power minus sine distance. So basically in general form that is e to the power minus x. Now, on the right hand side, if you can see the graph for e to the power minus x, this blue line is the one that we'll be concentrating more. Okay, so here you can see that blue line is actually, or I mean to say that this exponential of minus x is always a positive value. That means it's always greater than 0 when e to the power minus x is greater than 0, when x is actually approaching towards infinity, right? And other than that, it is having positive value. So e to the power minus x is always greater than equals to 0. That is for sure. Okay. So now if we go and if you see like what are the other thing in this equation, so we have log of 1 plus e to the power minus sine distance. Now we know that, so we know that this e to the power minus s is always greater than equals to 0, right? So log of 1 plus e to the power minus x will always be greater than equals to 0, right? Because the minimum value for e to the power minus x will be 0. So log of 1 will be 0. So now the summation, okay, let me just clear it. So the whole summation value will be always greater than equals to 0. We can conclude like that. Now, what is our optimization function? What it is trying to achieve is that we have to find out the argmin, that is the minimum value of, the minimum value of this whole function for, the W which is achieving it. So you have to find out the minimum value. So from this analogy, what we can see that the minimum value is actually 0, right? It cannot be negative, right? So the minimum value of this summation will be 0. It cannot be negative. So that is the best minimum value we can get for this summation. So our optimization problem, what it will try to do, it will try to reduce that summation to 0 because that is the most minimum value we can achieve. Okay. So how we can do that? So when the summation will be equals to 0 or it will achieve the minimum when this summation will be 0. So because when this log of 1 plus e to the power minus sine distance will be 0, and when it will be 0, when this particular term e to the power minus x will be 0, and when e to the power minus x will be 0, when this particular sine distance term will tend to infinity, right? So now if you think logically, this sine distance term consists of three things. One is yi, one is the weight vector, another is the feature vector xi. So out of these three, yi and xi are fixed. That is the data points we are given. We cannot do any changes on that. So the only variable is this weight vector, right? We can change the weight vector so that the total distance sine distance term will approach to infinity, and when it will approach to infinity, e to the power minus sine distance will be 0, and the overall summation will eventually become 0, and we will get the arg minimum, or we'll get the minimum value for this summation, right? So the thing is that to get the minimum value for this summation, w needs to be tend to infinity. W should approach towards infinity. Now, don't you think this is alarming? Because the weight vector value is infinite or a large value, right? So now just think it, I mean, the weight vector, that means the hyperplane is trying to get a best value for this particular feature vector, right? This xi. Because of this is the training data, right? So W will always try to be infinite or a very large value based on the training data and eventually make the model overfit. And what we know about overfitting? That in overfit, the training error will be very minimum, but the test error or the error when the model will see unknown data or future data, that error will be maximum. So for this particular, okay, so for this particular optimization, what it is trying to do, W is trying to, or W is actually approaching towards infinite or a very large value to make this summation minimum. And it is trying to do that based on this xi, based on this xi, which is the training feature or the training data. So eventually it will make our model overfit. It cannot be generalized, and if you try to productionize this logistic regression model, it will be a mess. It cannot do proper prediction for the unknown data, for the future data, for the test data to be specific. So what we have to do, we have to somehow bound this W to be kept on increasing and approaching to a very large value, that is infinity. We have to bound this W, right? So what we can do, the thing by which we can actually regulate this thing is called the regularization technique. And here in this particular slide, we will be looking for L2 regularization. So what we have done a small changes in our optimization function. So now what we are trying to do, we have added another term that is called the regularization term. Okay. Okay. So now the total function is split into two parts. This is called the loss and this is called the regularization term. Okay. So what I have said, our optimization function has now two terms. This is the loss term and this is the regularization term. And particularly this regularization is called L2 regularization because it is actually getting the L2 norm of the weight vector. So what is this? Lambda times summation j equals to 1 to d wj square. And what is this d? D is nothing but the dimension of the feature vector. I mean, ultimately, after solving the optimization problem, what we will get, that is nothing but the optimal W, optimal weight vector. And that W will be of size D. The dimensionality of the vector will be D, which is exactly equals to the dimensionality of the feature vector. I mean, that should be, because otherwise this dot product W transpose Xi won't be happening, right? Because both the dimensions are same and that's why this dot product is happening. So what we're trying to do, we are adding an independent term summation j equals to 1 to d wj square. This is actually the L2 norm of W. So that's why the regulation is named as L2 regularization. And lambda is nothing but the regulator, or better to say the hyperparameter. So in logistic regression, the hyperparameter is lambda. Okay. So in k nearest neighbor, we have seen the hyperparameter is k. By tuning the k, we can get the best out of the KNN model. Similarly, by tuning this lambda, we can get the best logistic regression model. Now let me tell you how. Okay, let me tell you how this regularization is actually working. Okay, so previously what was happening, to minimize that, W is tending to infinity or a very large value. Now there is another W term in this function, right? So if this W is tending towards infinity, this W will also tending towards infinity, and eventually will not get the minimum value of the overall function, right? Now the overall function has been changed. We have to find out the minimum of this whole function, right? So now if this W from the loss term, this W is trying to get the minimum value, and it is for that it is approaching to infinity. This W is the same, right? This W will also be increased to towards infinity, and eventually the minimum value will be disrupted, right? So the regularization W, it will try to do, it will try to be zero, right? It will try to be zero. Because if it is 0, this term will be minimum. Look, both the terms are trying to individually get minimum values. Now this loss term, if it is trying to get minimum value, W should approach to infinity. And if this regularization term needs to be get minimum value, this W should approach to 0. So actually there is a tug of war happening between these two terms. Both the terms are trying to balance each other. What is that? Both the terms are trying to balance each other. This loss term W is trying to get infinite value. The regularization W is actually balancing it. And the regularization W is trying to get the value of 0. The loss term W is trying to balance that. So there is a tug of war kind of thing is happening between these two terms. And eventually it is getting a proper fitting, or it is getting a proper W. Okay. So now how should we regulate that? That regulation parameter is lambda. So let me tell you how. So if lambda equals to 0, then there is no regularization term, right? If lambda equals to 0, then there is no regularization term. So it will be similar to the above optimization function, right? So it will be overfit. Now if lambda is infinite or approaching to infinite, then this particular regularization value will dominate this loss value, and eventually it will underfit, because in this regularization term there is no features, right? There is no training data, there is no training features, right? There is no excise, right? So eventually the effect of the training data or the feature data, the feature vector, will reduce drastically, right? So in that case the model will tend to underfit. So if lambda is 0, the model is going to overfit. If lambda is infinite, then the model is going to underfit. So we have to maintain a value by which we can choose the best lambda to best fit our model. Okay. Similarly, what we have done in our KNN. So this is what regularization does in general. It does not allow any model to get overfit or underfit. It gives you the best fit. And the regularization here we have learned that is called the L2 regularization. So similarly, there is another kind of regularization that is called L1 regularization. So everything is similar here, what I have explained. Instead, if you see the optimization function, now the regularization term has been different. Nothing different, like previously it was summation 1 to d wj square. Now it is getting the absolute value of wj. Both the regularization L1 and L2 are doing the same thing. It is trying to balance each other. The loss term and the regularization term is balancing each other, and lambda is the hyperparameter. Instead of doing the square, we are getting the absolute value of w, right? So this is called the L1 regularization. And one thing to note is that L1 regularization it should be creates sparsity by setting zero value to some weight values corresponding to less important features. So basically what we are having, we have feature vector, right? We have feature vector. We have F1, we have feature 2, something that, right? We have feature D. Similarly, we'll have the same weight vector, right? For feature 1 we have weight vector 1, for feature 2 we'll have weight vector 2, something like that. So if you think carefully, or if you think logically, all the features in a data set is not important. Some of the features are more important, some of the features are less important. Now this L1 regularization, what it is doing, it is actually setting zero value for those weights whose corresponding features are less important. Let's say if f2 is less important, then in the optimal value the w will be 0, or this particular w value will be 0, not the vector. Okay, the particular w value in the weight vector will be 0, because every w value has a corresponding feature, right? So if a particular feature is less important, the corresponding w value will become 0, and that creates sparsity. Sparsity means, if I say a vector is sparse, that means if the vector has 10 thousand elements, or say thousand dimensional vector, then maximum elements or maximum dimension is 0. Say 700 elements or 700 dimensions are 0. Rest 300s are having some values. So that is we call sparsity. So L1 regularization creates sparsity like that. Basically, L2 regularization also does the same thing. For less important features, the corresponding W value, it makes some small values, but not exactly 0. But L1 regularization does it. It actually creates a sparse vector. Okay. So this is the L1 regularization. Now there is something called a combination of both. That is elastic net regularization. That means a combination of L1 regularization and L2 regularization. Okay. So the optimization function is that this is a loss term that we know. This is lambda 1 wj square. That means this is the L2 regularization. And this is lambda 2 L1 regularization. So we are getting benefit from both the regularizer. And now we have two hyperparameters, W1 and W2. So by hyperparameter tuning method, we have to get the best combination of lambda 1 and lambda 2 for which we can best fit our logistic regression model. Okay. So in the next video, I will show you how you can do the hyperparameter tuning for logistic regression model. So here in this video, we have learned how to good fit our logistic regression model by using regularization term. Now, what are those regularization terms? L2 regularization, L1 regularization that creates sparsity in the W vector, and we can get the combination of both that is sometimes also called as elastic net. So this is the end of the video. If you like this, do subscribe to my channel for future videos and also share with your friends. Till then, have a nice day and happy machine learning. Thanks much for watching.